conversations about science with the scientists themselves. It's the place to be to talk science. This is Coffee and Science with your host, Rob Parks.
Howdy, y'all, and welcome back. And thanks to Steaming Cup of Reason, Jeff, for making that intro for me. Because the nature of this show is changing, less from a conversational point of view, like interviews, that sort of thing, more to just sort of topics in astronomy that may lead to open questions. Might need to find another intro, but who knows? But hello, Judy. Welcome. I was wondering if Dr. Wells would be in the house. Excuse me. So let me do this. Yes. Okay. So yeah. Howdy, y'all. Hope you all are doing well. Actually, I think I'm going to minimize my screen so I can see the chat, even though it makes my face really white. So yeah, I've completely lost my train of thought. All right. So yeah, I've been. So what am I going to do? What am I doing? Why am I here? The fun or the universal questions of life. Who knows? Are we being spied upon by the Chinese or aliens or whoever it is that's continually sending balloons into the North American airspace? Judy, no, we will not be hearing from Whitsit. I will not be showing any of his clips or anything of that nature. Primarily because I couldn't be bothered. So I've been this stream has been delayed. Originally, I had scheduled it for the sort of normal time of 10 in the morning on Sunday, but because of life, I didn't really have the time, or didn't feel like I had the time to basically invest in the pieces of evidence that purportedly come from him in regard to whether or not astronomy has a redshift problem. Unfortunately, like I said, life got in the way, and even now, I wanted to approach this in a little bit more cogent, a little more concise way, but we're going to basically just play it by ear and see what happens. So, where did this all start, really? Well, so Austin Whitsit, or Whisit Getsit, for those of you who are not part of the debunking community or what have you, is a gentleman, a YouTuber who has, although I don't know if he actually makes content anymore. I know that he's making the sort of debate circuit, and he's on Discords, particularly Cosmological Tartaria, but I don't know if he's actually making content anymore. But regardless, he is a gentleman who believes that the Earth is flat, and he believes in that gravity can be explained through electrostatics. I'm not going to get into that because, there's a lot to dissect on that. But I had the privilege of speaking with Whitsit directly on the cosmology the Tartaria. I know I'm going to butcher that name. That server. I actually spoke to him directly. And he, I don't remember how it really got started, but he got on to that essentially. Oh, no, I remember how it got started. It got started because I was talking to someone who was putting forward that the Earth was concave. It wasn't flat. It wasn't a globe. It wasn't convex. It was concave. So imagine we're living on the inside of a sphere, and that the night sky and the celestial sphere, as they call it, are at the center. And so the question that I posed, and I really do want to pose this to to a concaver, I guess, at some point, is where is universe? Where are the galaxies? All that kind of good stuff. Man, I am really washed out. Where are the galaxies? Where? And I use the word redshift. I basically said, how does the concave universe explain the redshifts that we see, that astronomy sees everywhere? And that's when Whitsit popped up, or piped in. He basically told me that that astronomy, there are many redshift anomalies out there, and the CMB basically debunks the Big Bang. He put forward that both these redshift anomalies and the CMB, the problems that he sees with the CMB, essentially negate the Big Bang theory. And so I was like, all right, well, the CMB, no, that's just wrong. His understanding of the cosmic microwave background is just incorrect. He refers to something called the axis of evil, which, if someone in my comment section or someone here can point me towards a source other than the very thin Wikipedia article, I would very much like to look at it. What the axis of evil briefly, well, actually, let's back up entirely. And folks might be wondering what the cosmic microwave background is. Well, in a nutshell, when the Big Bang happened, it was, as far as we understood it, when it became large enough for our physics to understand what was going on, the universe as we know it can be described as a very hot plasma, or very hot energy field, which as it expanded outward began to cool. And from when it cooled, Dr. Well, or Clive, I'm sure you have a much better explanation of this, but essentially, when the universe expanded and it cooled, things began to condense out of it. And then we got, the quarks, we got leptons, then we got atoms, then we got stars, and we got galaxies, yada, 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 yada. Well, that energy, that's what happened to part of that energy. Part of that energy went into basically matter. The rest of the energy, the background field of energy that was released when the universe became essentially transparent enough for that energy to move out without very, very quickly running into something, that just moved outward. And as that energy propagated outward, the energy of the universe expanded, and the energy became redshifted. So the Big Bang predicted that, given what we see, given the borderline conditions of what we see today and what we believe it should have been back then, we believe that the universe, that there should be a microwave background that has a temperature of around 2.7 Kelvin. It has a black body spectrum of 2.7, corresponding to an object radiating with a temperature of 2.7 Kelvin. Starting to get a little ahead of myself. What that means is that essentially background space, like when we think of, when some sci-fi would have you believe that if you get in the deepest, darkest regions of space, it's going to be absolute zero. And no, that's not true. Actually, quite different from that. What astronomy tells us is that in the deepest, darkest regions of space, where there's very, very little light or any sort of energy from any outside point of view, the universe has a temperature of 2.7 Kelvin. That is the background, or the leftover radiation from the Big Bang. If you were to collapse the universe down back to its original starting point, that temperature would be ginormous. Because essentially, if you squash something, that something tends to get hotter. Anyway, the CMB, as cosmic microwave background, or CMB, is one of the most beautiful pieces of evidence in science. It is gorgeous. What I mean by that is if you look at, obviously I can only speak to astronomy and a little bit of physics when it comes to reading papers, looking at correlations, that sort of thing. When you look at these sorts of things, you have you obviously have the data that you receive, that you measure from some object, observations, what have you. You have some data. And then you have an underlying model, which is how you are describing that data. And, inevitably, you're going to have scatter. You're going to have some kind of disagreement between the data points and your model. Hopefully, and that's where the error bars come in. I mean, essentially, you'll fit your model to those observations, which have error bars, and you try to get that model to fit that data as best as you possibly can. And depending on the quality of that fit, that tells you how much confidence you have in accepting that model, that description actually fits with what you're seeing. So for instance, in this case, we would create a model of the Big Bang and basically scale it out to our present epoch. And then we apply that model, that curve indicating the temperature, to the observations we extract from the CMB, and we'd see how good the fit is. I have never seen a fit that good anywhere else. Actually, let me see if I can pull it up. And this is just unbelievable. Oh, I'm gonna get clipped. I know I am. People are gonna be like, "Oh, look, he says it's unbelievable." So we can't believe it. Here we go. So I probably should choose my words a little bit more carefully. Let's share my screen. No, tire screen. Let's do that. Probably a bad idea, but sure. Or no, it won't let me share my screen. All right. I guess because it doesn't want a inception event or what have you. So I'll just do it this way. There it is. There you go. So the dotted point, the dots correspond to measurements taken off of the cosmic microwave background as imaged by, what is this? Kobe data? FRAS data. Huh. It's Kobe data. Okay. So this was Kobe, the Cosmic Background Explorer. This was actually the first attempt to image the cosmic microwave background all over the sky. We have since made even better maps. WMAP came a decade or so later. Then a few years later after that, we had Planck. It is extremely, how should I put this? We have very, very accurate measurements of the CMB. And like I said, this is the first pass. So our measurements have only gotten better. So their error bars are smaller. You can see here, the dots correspond to, like I said, that temperature or that temperature profile that we extract from the CMB. And then the black line corresponds to the theory. Basically, Big Bang tells us to expect that line. Down here are what scientists refer to as the residuals, meaning basically you take the residual is how far off from that theoretical line is your data. So if your residuals are large, that indicates that your fit is not very good. And so therefore you should have very little confidence that your model is accurately explaining what you're seeing. Here, and these, pay attention to the y-axis. This is Jansky's per steradian. That basically means amount of energy per area on the sky. These are the same units. So here you've got this goes from 0 to 400. These residuals are on the order of 0.05. So 1 part in 100. These error bars, you could theoretically plot them on this plot, but they would be so small as you would not be able to see them. This residual plot is actually necessary to show others that, yes, we have error in our observations, and yes, we are accounting for that. This data, this fit is just, it is beautiful. It is something you dream of your data fitting this well to your model. So nice. Got to see John Smooth. Did you get a chance to watch that video on? No, unfortunately, Clive, I was not able to see that yet. But thank you for putting that back on my radar. I want to check that out. So, why do I keep bringing all that? Why did I bring this up? Well, let me show you. Let me see if I can show you. All right, there we go. This is this Planck? Oh, this is 2013. So, oh no, I got it backwards. Sorry. It's Kobe, then Planck, then WMAP. Anyway, this is sufficient. What you're seeing here is the deviations in temperature from one point to another. So the cosmological principle that we have, good point. Errors are seeds in galaxy formation. That is a good point. Thank you for catching me on that. So really what I should say is that what you're seeing here is the red points are areas of slightly warmer temperature. The blue areas are areas of slightly cooler temperature. Is it Kobe? Was Planck back in 2013? I thought it was Kobe, WMAP, and then Planck, but I didn't realize Planck was that long ago. Ah. So like I said, red is hot, blue is cold. But again, the variations are freaking tiny. But the cosmological principle tells us that the universe has to be, or is, isotropic and homogeneous. What that means is that if you were to look at any particular large region of space, and the number that people throw around is about 500 megaparsecs or 500 million parsecs, or divide that by 3.26 and you get light years, somewhere in there. So we're talking about a large volume of space. When you look at that region of space, and you can look at any region anywhere, and you compare those two particular regions, they're essentially going to have the same bulk characteristics. The amount of energy and amount of mass energy located in that region is going to be the same. The density is going to be essentially the same. And so basically everything is the same no matter where you go. Obviously, there are going to be, the universe is clumpy. And so if you look at smaller spatial scales, like if you looked on the spatial scale of, say, the local group of our galaxies, yeah, obviously there is, differences between if you look at one region of space as compared to another one, particularly if there happens to be a galaxy in one and not in the other. But if you look on a large enough spatial scale, then everything should be homogeneous. And it should also be isotropic. And what that means is that it looks the same no matter where you look. You can look at two blocks of space over here, and you can compare them, realize they're both homogeneous to each other, and then you look at two blocks of space over here. You say, oh yeah, they're homogeneous to each other, but they're also, basically the same as stuff over here. No matter where you look, it's the same. There is no preferential direction in space. There is no preferential location in space. The CMB is an excellent example that illustrates this point. If you look at this map, on a large scale, it is homogeneous. No part is any different from any other part. Like I said, on a large scale, and there is no preferential direction. Essentially, it's not hotter on one side of the map than it is on the other. Well, Whitsit believes in, or has posited, this thing called the axis of evil, which the only other person I've heard mention this is a gentleman by the name of S.C. Montreal. He was the first person to put me on this. And I looked. I'd never heard of this axis of evil outside of World War II and also Bush W. I've never heard of this idea of axis of evil, particularly from a cosmological standpoint. No, I've never, it's not in a textbook I've read. It's never been in a conversation I've had with anyone. So I was like, what is this? So the only thing I could find was a Wikipedia article, which is very, very thin, that basically says that there is an anisotropy, basically a deviation from isotropy, or really a preferential location or preferential orientation in the CMB. And that preferential orientation just so happens to correspond with our solar system. And so the idea is that the axis of evil actually indicates that what the CMB is telling us is that we are in fact the center of the universe. At least that's what I'm getting from all of this. But again, I need to stress that outside of that Wikipedia article, never heard of this. I've never seen an article written on it, never read it in a book, never heard it talked to me by either my professors when I was a grad student or as one of my colleagues. Never heard of it. So I explained that to Whitsit. I'm like, that isn't a thing. I don't know where you're getting it from, but if you tell me that if you have evidence to suggest that this is something that is scientifically valid, that somebody is actually positing this, I will take a look at it and I will let you know what I think about it. But until then, you're just wrong. It's just not there. And then that came up to, the next thing came up was redshifts. He brought up the fact that there are redshift anomalies all over the place. And I was like, really? That is news to me. But I did have to, and what he means by redshift anomalies, or at least at the time what I got, was that he seemed to indicate, and I don't want to put words in the gentleman's mouth, but he seemed to indicate that there were problems in measured redshifts that could not be explained via either cosmological redshift or Doppler redshifting or any normal, or what we would consider standard idea of how redshifts are created. Like, that's interesting because I don't know of any. And then I thought about it for a second. And of course he lambasted me. How can you not know? And I was like, all right. Let me think about it. Oh, yeah, all right. I know of one, maybe possible or anomaly. And that's dealing with the supernova 1A observations. The supernova 1A observations are the observations that really pointed to the fact that the universe is not just accelerating outward, but it's accelerating at an ever increasing rate. It's doing something that we never thought was possible. Essentially what that indicates is that not only does gravity pervade the entirety of the universe, which is attractive, but there must be some kind of repulsive element, which is pushing the universe further and further away, because gravity is only going to want to bring this thing back down. So if you only account for gravity, there is no way for the universe to be accelerating at an accelerated rate. It's just not physically possible. So there has to be something pushing on it, or at least that's the idea, which then brings into dark energy. So I was like, all right. And I'll be the first to admit, this is again Whitsit. Yeah, I think so. I don't know what you mean by this, but yeah. I'll try to actually, let me switch this over so I actually look at the comments better. And I'll be the first to admit, I'm not a big fan of dark energy, because of the common science denier tactic of, I don't understand it. So if I don't understand it, I don't like it. But I don't go so far as to say that doesn't exist, that it's not possible. I just don't like it. And I would really like an explanation that makes more sense to me. And I'm not the only one out there, or really, I should phrase it in the sense that this is an extraordinary claim. This claim that there is something beyond gravity, and in fact, if you the analysis shows us that not only does dark energy exist, it is the dominant thing in reality. It constitutes 94% of existence in order to explain the expansion that we're seeing. So yeah, it's an extraordinary claim, and it requires extraordinary evidence. So obviously, scientists are going to do their due diligence, and they're going to say, well, wait a minute, maybe something's wrong. And the first thing you go to whenever you have a new observation that indicates something wildly fantastic, you say, well, are the observations trustworthy? Are the observations, are they real? And so there have been, we've looked into systematics of whether or not the observations suffer from some kind of systematic that means that the measured redshifts that we're getting are far too large, or just systematically larger than they should be for that distance. As far as I know, the observations, the methodology checks out. There have not been any systematic errors identified. But, and this is the first time, I will probably repeat this many times, I am not a cosmologist. This is not my field of expertise. I am not up on the cutting edge research. So there may have been a discovery, or there may be something out there within the last 5, maybe 10 years that I just simply don't know about. But to my knowledge, and again, I'm thinking that if something like that had actually occurred, if someone had found, oh yeah, the whole idea that the supernovae are moving faster than we predicted is actually bunk, I think I would have heard about it. I think that would have gone around the lunchroom table. Anyway, so the point that I'm going to make is that scientists do their due diligence. So they first looked at systematic errors. As far as I know, they didn't find any. Then they were looking at whether or not essentially redshift, the speed of light, really, whether or not the speed of light was constant over cosmological time. Again, not an expert. I'm sure there are theories out there that posit that. Clive would probably have way more expertise on this, or knowledge on this, than I would. But my point is that yes, I'm like, all right, that is a redshift anomaly that I know of, is that these redshifts are telling us something that previously we thought to be impossible. And so Whitsit was like, aha, there is one. You admit there is one. Like, yeah, okay, there's one, but that has to do with supernovae at the edges of our universe. Like, what about everything else? And so he sent me some links on that Discord. I've been meaning to go back and actually look at them, but there was a gentleman, Eric E, on Blue Marbles Discord, who sent me a file. And that's what I'm going to be dissecting. So this might be a little bit dishonest of me, I guess. Not purposefully so, but might be a little dishonest because I haven't checked the provenance of these documents, that they are in fact what Whitsit claims. But what I can say is, by looking at them, that these documents do relate to redshift anomalies and the idea that the Big Bang theory or the Big Bang model is incorrect because of these particular anomalies. So, like I said, that's really what I want to get into. What I'm going to do is I'm going to look through them. Well, I've looked through them a little bit, but I just kind of want to go through them on the stream and talk about, as objectively as I can and as honestly as I can, I'm going to look at the evidence and tell you what I think about it. And if I think that this is legitimate, then I will say so. If I think it's being misrepresented or just garbage, I will say so. So, let's do this. Wonder if so I've got this file and I can share it with anybody who wants it. Really what I would do is I would actually share with you the relevant pieces of information, because there's a lot of strange stuff in here. Let me see if I can share my screen on this. Nope, wrong button. Like almost comically weird. Nope, I'm not going to be able to show it. But, so, all right, so I've got this. You're going to have to take my word for it, because apparently I can't share my entire screen. Sucks, man. It sucks. Entire screen. Or maybe I can. Aha, I can. Look at that. Woo, Inception. So I don't know how well you can see this, but so this is the file once you unzip it and all that kind of good stuff. You got all this kind of good stuff. So I was putzing around in it. And I got to this and I looked at this and I'm like, all right, it's a whole bunch of, there's some PNG files. Sorry, my computer is taking forever to load. And so in his evidence for redshift anomalies, you get pictures of sell your online course in 7 steps. Okay. All right, that seems pertinent. So yeah, if you want this, I'll send you the stuff that actually is pertinent. But what really made me want really cautious about what I'm clicking on, I got to this. Well, first, it's a Bing webpage file, which I'm like, anyone who uses Bing is suspect. And I'm like, all this tells me, the first thing that popped in my head is, yeah, I probably should get my prostate checked. Again, what this has to do with redshifts, no friggin' idea. So anyway. So I'm going to boil this down. TLDR. What this boils down to, what all of this evidence boils down to, is essentially 2 anomalies. The first one is, and the bulk of what he is showing, is that if you look at the redshifts of quasars, specifically QSOs or quasi-stellar objects, I'll explain what those are in a second. If you look at those objects, particularly when they're paired with a normal galaxy, and what I mean by paired is that they are believed to be gravitationally interacting, they are believed to be in the same area or the same position in space, not just from an XY position, but also from a Z position. They're basically at the same distance. So Hubble law, the Hubble expansion, tells us that if something is at a set distance, then it's going to have a certain redshift. It's going to be traveling away from us at a certain speed. V, the velocity of a galaxy is equal to a constant, which now, unsurprisingly, is called the Hubble constant, times d. So that is essentially how we know. That is one of the primary mechanisms for how we are able to tell a distance at really, really far distances, at distances so far that we can't really use any other method, because that requires much more precise observations that we can make of said objects. So we rely on the Hubble law, the Hubble relationship, in order to really probe the distances out to basically the beginnings of the universe. All a bunch of speculative hogwash. Yeah. I'm going to try not to take offense to that, considering, you're basically besmirching, you're calling an entire field of science hogwash. But I will leave that for now, particularly coming from a gentleman who I've asked repeatedly to talk to on voice, and repeatedly he has not even bothered to say no. He just simply ignored me. So anyway, where was I going with this? So the Hubble law, found by Edwin Hubble, and again, I should be offended. Wow. All right. Like I said, I wanted to have a more cogent explanation, because again, I don't know. One of the other reasons why I wanted to do this, really the main reason, was to basically highlight certain topics in astronomy that people might find interesting, such as the Hubble law, the expansion of the universe, and all that. So in a second, I might actually take a step back and explain where the Hubble law came from, what its significance is, and so forth like that. But for right now, what I'm like I said, the TLDR version is that there are observed. Wow, there are observed. Oops. There are observed discrepancies between. So there are two objects. So if you have two objects in space, two galaxies in space at, say, 2 megaparsecs away, or 2 million parsecs away, 2 megaparsecs away, those two galaxies should be moving away from us with roughly about the same redshift. Not exactly the same redshift, because they have their own intrinsic motions, but they should have very, very similar redshifts because of the Hubble law, or because of the Hubble flow, or the expansion of the universe outward. And so there have been observations that indicate that there is a quasi-stellar object, a QSO, right next to a normal galaxy, and those two redshifts are extremely disparate. So obviously something is wrong. That cannot be explained simply through Hubble flow. Cannot be simply be explained as those velocities are being primarily caused by the expansion of the universe. So that's one. The second argument, or the second anomaly, which I've only found one reference to in this entire thing, is that there seems to be a discrepancy between the redshift that we would expect from looking at the sun. So the sun is rotating, and so it's going to have a certain redshift profile. And based on what we know about the sun, and we would expect that velocity or that redshift profile to look a certain way. And then we measure it, and we find, and apparently there has been an evidence or an indication that the two aren't the same. That our understanding of the redshift is inadequate to explain what we're seeing. Okay. Was not aware of this. Again, this is not hugely, this is not something that is widely talked about. And that I'll get there. I'll get there. First, let me do this. All right. Actually, I'm going to stop sharing that. I'm going to share that one. So it's bigger. So I keep throwing around this term redshift. I keep saying redshift this, redshift that. Professor Barks, what is redshift? All right, so redshift is I was trying to come up with something witty. Redshift is the apparent reddening of light due to the motion of an object moving away from you. Now, we see this with most commonly with something known as the Doppler effect. Doppler effect tells us you have probably best experiences with sound. If a siren is coming towards you, then the pitch of that siren is going to go up. So the frequency of the sound is going to rise as the siren comes towards you. As the siren moves away, the pitch is going to drop. This is compared to if you were just standing right by the siren and the siren wasn't moving. So there's obviously what's happening is that the sound is propagating away from that siren at a set speed, and that the siren itself has a speed relative to it. And so when the siren is coming at us, then the wavelengths essentially get compressed. And when the wavelengths get shorter, the frequency goes up. That's what physics tells us. This is particularly true of light. So light travels at the speed of light. And what physics tells us is that the velocity of a wave is equal to the wavelength of the wave times the frequency of the wave. Since it's a constant, if the frequency or if the wavelength goes down, gets smaller, frequency has to go up. Physics also tells us the amount of energy being carried by that wave is directly proportional to the frequency. And so if the wave goes down, the frequency goes up, the amount of energy being carried by that wave also goes up. And so therefore it's going to appear bluer. So what we have over here, over the right, the animation that hopefully you all can see, are two stars orbiting around a common center of mass. This is what we would refer to as an SB2, or a type 2 spectroscopic binary. We see the absorption spectra of both the blue star and the red star as indicated by these dark lines running through this prism band of color. Here you can see that this is the observer, the green dot over here. The blue is traveling towards us. As it does so, the red is traveling away. This is too fast for me to really comment on both in real time, but hopefully you can see that there is a contrary, an opposite. So as one moves forward, the other one moves away. And what you can see is that the lines, which correspond to, in this case, this B is the lines for the blue star or the red star, the A are the lines from the blue star. You can see that they move back and forth through each other. This is the redshift effect. This is the Doppler redshift. This is a actual example provided by the European Space Agency, go ESO. And what we see is that in the lab, we have pretty much determined the spectra of every chemical element that we know of. That's on the periodic table. And exhaustive work has been done to categorize all of these different lines that we see in these astronomical spectra. These astronomical spectra serve as chemical fingerprints. No two spectra from two different elements is exactly the same. So here, and I have to admit, I don't know what element this is. But I can tell you it ain't hydrogen and it's not helium. But anyway, whatever gas this is, it's going to have these lines associated with it. And we know the measurement, we know the positions. Howdy, Nimrod. Howdy, Norm. Thank you for coming. We have the line positions. We know those exceedingly accurately because we can do that in the lab. We can measure these in the lab exceedingly accurately. And so when we see a spectra of a star, we can identify where those lines are. So you have this dark line here. This line corresponds to that line. These two over here correspond to these two over here. And what we see is that this spectrum has shifted. Now, one might ask, how do I know that this line corresponds to that and this line corresponds to that one and so forth? The way that I know this is that redshift will affect all lines equally. So if I look at the distance between these two lines and it says the distance between those two is a wavelength difference of 100 nanometers, and I come up here and I say, oh, look, this line and this line over here, they have a difference in wavelength of 100 nanometers. Pretty safe bet they're from the same element. And then when you do that for all of these different lines, then you're positive that what we're seeing is this element in this star and those wavelengths are being shifted to the red. You might be asking, Dr. Rob, what are all these other lines? Well, those would be other elements in that star. A star is not a singular object. It's not a monolithic object. It's not monoelementic. It's composed of many different elements, not just one. And so depending on the shift, that's going to tell us how fast the object is moving. And then that's going to give us something known as a redshift, which is designated as Z. And that is the velocity of the object with respect to c, the speed of light. And so in future plots, you're probably going to see this factor Z popping up quite a bit. And so this will be an example of the Doppler effect causing redshift. Basically, the motion of the object moving away from us because of its intrinsic velocity. Then you have what is known as the astronomical redshift. Now, the astronomical redshift is the same observed phenomenon, but now the redshift isn't due to the shift isn't due to the intrinsic motion of the object. The redshift is not due to the intrinsic motion of the object. The motion is due to the fact that the universe is expanding outward. Very much like if you took a balloon and you put dots all over the balloon and then you inflated it. So, well, first you put dots all over the balloon, you measure the distances between those dots, and then you inflated it and you measured those again. You'd find that all of those dots, the distances between them would get larger because they've all expanded away from each other. So you've got this, which is also known as the Hubble flow. And then you've got, here's a nice example of what I was talking about. This is the raisin cake, whatever, example of it. And then you've got, it doesn't have it in here. Then you've got something known as gravitational redshift. Now, I'm probably going to mess up this analogy, but this is the way I look at it. This is what I believe causes, or this is the way I explain gravitational redshift to my students. Remember before when I said that the energy of a wave is directly proportional to the frequency, and that and that redshift or that wavelength and frequency were interrelated to each other? Well, so I like to use when gravity is put out there, it is frequently talked about as, something is sitting in a gravitational well. So I really kind of latch on to that idea is, all right, if I'm in a well, or if I'm at the bottom of basically a hole, really, with shallow walls, if I want to get out, if I want to go up to a higher elevation, then I have to do work. I have to expend energy to go up that slope and get up to that higher elevation. So in an analogous way, normal people, yes, respondents man. So I have to expend energy to get up to that higher level. And so in a similar way, an analogous sort of way, if you were to turn a light flashlight on and point straight up, that light is battling against gravity. And so it loses energy because it is essentially doing work to get up higher, to move away from the earth, to move out of that gravitational well. And so if the light loses energy as it's fighting its way past or through gravity. I know this is probably a horrible analogy, but this is like I said, this is the way that I explain it to students: is that the light does lose energy as it moves through the gravitational field. It moves away from the Earth. And depending on the strength of that gravitational field, essentially the depth of that well, I like to think of it as the slope of that hill, as it were. You know, if you've got a gentle slope caused by something that doesn't have a lot of mass, then it's pretty easy. You don't have to work so hard to get away from it. If you got a higher mass, if you got and the slope is steeper, then you got to work even harder to get over it. If it's basically like a black hole, such that the mass and the radius are the mass is so big and the radius is so small that the slope of that hill is now damn near straight, a vertical, then obviously no one has enough energy to get up and get out. So that's gravitational redshift, is that light will lose energy as it basically fights against a gravitational field to get away from a massive object. So those are the three types of redshifts that we really want to talk about. So what about these anomalies? Well, where was it? So I'm going to actually start off with the bit of evidence that I thought was actually that got my attention. That was like, hey, this is worth looking into. So so included in this is a paper by when I share the screen, I will let you know because I can't pronounce the person's name. How about this? Nope, wrong paper. Can I share this? Aha. All right, so this is the paper that Gary was here. He basically came here to insult me, and then I don't know, he may have left. And so this is the paper that is included in this zip file. It is by Alessandro Trinchera. Again, I'm probably butchering the name. Now, a couple of things pop out at me, and again, this is I'm putting on my astronomer scientist hat. So whenever I look at a journal entry, or whenever someone sends me a journal, or I find a journal article somewhere, these are the things that immediately just kind of go off in my head. Basically, as red flags to tell me whether or not I should, whether or not what I'm about to read is problematic. The first one is the fact that this is a paper on a specific topic, not a review article, but a paper about a very specific topic that is single author. That speaks of quackism. Usually, if you have a single author paper out there, this is something, again, that is not a review article. A review article is basically, occasionally someone will say, what is the current status of Redshift anomalies in the literature? Or more specifically, like what is the current status of exoplanet research in the literature? So somebody will take it upon themselves to collate all of that data and provide a nice review article for the community. That's not what this is. This is, again, specifically dealing with a redshift anomaly on the solar disk. And this, I think, is really the teaching part of it, is this is how science is actually done. Science is not a one-person operation. You work in collaboration. Now, there are two major reasons that I can give you for why you want to work in a collaboration, why it is most beneficial to do science as a group rather than singly as a single person. The first one is the more pragmatic, I guess, is that when you're talking about scientific topics, usually, you obviously want to get the biggest bang for your buck. You don't want to just put out a whole bunch of mealy little papers here and there. You want a paper that has some punch to it. You want to have a paper that has a lot of impact, and that means that you're going to be looking at the problem through various different sort of perspectives, and some of these perspectives may not be exactly in your field of expertise, or it just may require a lot of work, and so you divvy up that work. You basically, professors will assign projects to grad students, or postdocs, postgraduate researchers, particularly if it's in a field where, if I'm doing, for example, I wanted to do a multi-observational study of star spots. I would and I want to basically characterize them. Then what I would do is I would do it interferometrically. I would use an array of telescopes to look at it using one technique. I would then get another astronomer to look at the same object photometrically, then another astronomer to look at it spectroscopically. We would do the analyses of these on our own, and then we would send each other the data, the final product, and then the lead author, the person really the principal investigator or PI, is going to put all that together in a nice, neat package and write a paper about it. Oh, and mathematics single author papers are common. I don't doubt that. Mathematicians are a little kooky in my opinion. No offense, Clyde. But in physics and astronomy, a single author paper is anomalous. Is an anomaly, really, in and upon itself. Because, again, like I said, you want to do science in a group because, again, you want to divide the labor. And particularly if you are dealing with techniques, scientific observational techniques, or scientific or modeling techniques that you are not exactly an expert in. You want to hand that off to someone who is, so you have the best people working on the project that you can get. So lots of people. The other thing, and this is really the reason for why I feel is a red flag that you see single author papers on physics and astronomy papers, is because you need that collaborative work as the first sanity check. So debunkers and I will also go on tangents about how important peer review is. When you send out a paper, you want it to be reviewed by the community. And yes, there are definitive flaws in that process, flaws that we are constantly talking about and constantly working on. Whether or not the reviewer should be anonymous is a big one. I'm getting to that, Respondus. I'm getting to that. So the review process is not perfect, but it's the best that we have. But even before you get to the review process, even before you send it to a journal, you send it so that someone else in the field can actually look at it and analyze it. You have your own research group. So if any particular person goes off and is like, hey, look, aliens, the other people can be like, no, not aliens. That you can have a sanity check within the group to cut out any kind of really weird tangents going off. So if you're a first author, or excuse me, if you're a single author, you don't have that buffer. Now, obviously, there are plenty of examples where research groups are echo chambers or Discord servers or echo chambers. So you obviously need that peer review, but in the best of circumstances, that research group should, in fact, provide some kind of first order sanity check. Now, responded, yes, alien. Yes, aliens. Actually, you guys are getting ahead of me. All right. So is the Gmail address a red flag? Absolutely it is. I had to look this up because I was not overly familiar with the Journal of High Energy Physics, but yes, apparently it is a respectable journal. It's open access, which I'm all for. And I was like, all right. So, which makes this next bit kind of impressive because a reputable journal really doesn't want to take research from average person on the street because of the quality of science that can come out of the average person on the street. So you really, really got to impress the editors. I'm assuming. I don't know the specifics, obviously, of this case, but I would have to, from my own experience and from what I know of how these things work, Alessandro impressed the editor of this journal enough that they were like, all right, I know you do not seem to be associated with any academic institution. So you're obviously doing this by yourself without any sort of collaboration, obviously, first author or only author. So it must actually, the paper must actually have to be, getting to that too. The science might actually have to be good. So I'm like, all right, that's actually kind of a reverse red flag in that a good journal or a good reputable journal actually posted or published a paper written by ultimately a layperson. And I did ultimately Google Alessandro because one of the things that I did was I also Googled Redshift anomaly in the solar disk because I read through the paper and I'll go over it in a moment, at least cursory. I'll go over it. And I looked through it and I was like, wow, this isn't garbage. This is again to first order from just skimming it, reading through certain bits. This is rigorous work. This is not just hackery. So I'm like, all right, so maybe there's something to this, and I just haven't heard of it. So I Googled Redshift anomaly in the solar disk, and the only articles I could find related to this subject were by Alessandro. So I'm like, okay, that's a red flag. If only one person is talking about this, something's going on. So I looked into them, and it's interesting. I have a theory, as it were. Excuse me, that's not scientific. I have a guess, as it were, about what's going on here. So this is Alessandro Trinchera's Facebook page, or not Facebook, LinkedIn page, which looks to be current. Thing I popped out is that he's a mechanical engineer, or at least mechanical designer. So Alessandro's background is not in physics or astronomy. He's an engineer. I'm like, oh, all right. Well, that's interesting. Well, that's kind of that kind of made me question And then I was like, oh, wait a minute. This person's now a master's student at the University of, Tübingen. I butchered the hell out of that. Is now a master's student. He's actually at a credible university. And the papers that I've seen other papers that I've seen subsequent actually have Alessandro associated with that university. So what I'm guessing is, and this is pure speculation, is that Alessandro is an intelligent individual, knowledgeable in this field, or at least, self-knowledgeable in this field, probably didn't learn about it through YouTube videos, and decided, hey, I'm going to take a crack at this. Hey, Einstein was a patent clerk. So Alessandro was like, hey, there seems to be a problem. Let me see if I can solve it. And voila. Because of an author's. This was an issue the other day when a Flurf was criticizing the peer review process because the author's possession of a degree was a prerequisite for submission. Yes, and I do want to talk about this because from talking with folks on Flat Earth, I understand this grievance, and I understand that there does seem to be this bias against layperson, or this idea that if you don't have a degree, then you aren't worth talking to, that your ideas aren't worth anything. I think this is with most things Flat Earth, this is a nuanced conversation that needs to be had, and I need more coffee, is that if you don't draw a line somewhere, then let me back up a second. I'll get this. I'll get to that in a second. I have not a degree, but I've had to provide evidence for I work for an institution. And so obviously, as I published, my first paper I published, I was not a doctor at that point. I was still a grad student. So it wasn't the degree that needed to happen. It was the association with a Institute of Higher Learning. But what I wanted to say on this, and I want to be as specific and as careful as I can be with this, is that everyone has horrible ideas. And a lot of people believe that they are entitled to those ideas being taken seriously. Okay. The where it comes into these journals and where the scientific community comes from is that being associated with an institution, being associated with or having a degree, these are sort of a first cutoff, because there are a lot of ideas out there, some great, some horrible. Some of those great ideas are by lay folk. Some of those horrible ideas are by PhD having professors, as I'll point out later on. But there needs to be a cutoff, because if not, you're going to be inundated by a whole bunch of stuff that just doesn't make any sense, just isn't good science. And so you need to have some kind of bar upon which to basically establish yourself. And so the reason why I'm really highlighting this is to show you that apparently that bar can be overcome. That if you are someone who is self-taught and you have an idea about how to solve something, you can do the math. You can write the paper. You can do the modeling. You can basically, that's what this person did, was he did the modeling. This was not, he didn't have access to the fancy equipment. He did, basically it was all mathematical models. And he got it published. He got it published in a respectable peer-reviewed journal. So it is possible for that to happen. But the science has to be good. And yeah, is that a bias? Is the bar higher for people who are not part of a academic institution? Yes. Is that fair? Probably not. Not completely. Is it necessary? I think so. Because again, if not, you're going to have some really, really whacked out ideas that are not supported by evidence or mathematical rigor or really any kind of I don't want to, by evidence or mathematical rigor. So I think it has to be that way. If there is is there a better way? Probably. Have we figured it out yet? No. This is the best way that we have so far. So, so where was I going? So let's talk about the paper in brief, because again, it is a theoretical paper, not my field of expertise. I do know more about the sun than I do about than cosmology, so I can put you in there. So what I'm rambling about at this point is I can't tell you about the math. I can't tell you whether or not the math is correct. I can tell you whether or not his methodology is sound enough. Maybe Clive I'll send the paper to Clive and he can dissect it. Where is it? It's there. All right. So let's talk about the paper itself. So starts off by saying, talks about this new tired light theory. Tired light, it's in capitals. I'm like, all right, this is weird. So I looked it up, and there's something in the back of my head that was like, this sounds like something I've heard of. And what the tired light theory is a rebuttal against an expansionary universe. In essence, and again, I don't know near enough about it because it's not taught. It has essentially what I looked into is essentially been debunked or put on into the fringes since think the late 60s, early 70s. And really the CMB cannot be explained via this this model. But the new light, the tired light theory essentially boils down to is as light passes through space is not a perfect vacuum. No space is a perfect vacuum. It's going to run into stuff. Particularly, it's going to run into electrons and protons, positively charged particles. And in doing so, it's going to give off some of that energy during that interaction. There is a physical basis for this. Bremsstrahlung is a good example of this. There are interactions that we see in everyday science that go along with this idea. But the problem is, the things that this tired light theory needs to explain are one, very broad stroke. One, why is it that that the energy, that light always loses energy? Because when we look at cosmological distances, we see redshifts. We don't see blue shifts. We see redshifts. So why is it that all of these interactions take away energy and never give energy? Why is it always a deficit rather than, because when you talk about interactions between particles, the energy isn't destroyed, it's transferred. So if the light can transfer energy to the electron, then the electron can just as well transfer energy to the light. So why don't we see blue shifting? A. B, can this theory, which requires a certain density of electrons, a certain medium, which is probably why Whitsit loves this theory, because it basically postulates that light is traveling through a medium of charged particles. Again, electrostatics. I will put money down that you will be hearing about the new tired light theory from Whitsit and Co. over the next month. I do not doubt this is the direction he's going. So you heard it here, folks. You heard it first here. Whitsit is going the new tired light theory direction. And so the medium has to explain basically the amount of redshifting that we see, obviously. So the amount of electrons. So for a given, presumably for a given density of electrons, you're going to have energy loss for the light that passes through it, and so it's going to, as energy density gets higher, then we should know, the theory should predict how much energy is being lost, which there again will predict how much velocity is being lost, and so forth and so on. So basically you can take that idea and actually apply it to the observational data rather than just saying it's a good idea. Cannot be explained by the CMB, because the CMB basically it is Big Bang, cosmological redshift perfectly predicts a 2.7 Kelvin background temperature. Tired light doesn't. So that's the big kind of nail in that coffin. The other thing that that was a bit of a tip off, or a bit of a red flag for me, is, when you write introductions, or when you put forth a paper and you put an introduction, you typically give a very short but very concise but thorough description of the problem. And what I mean by thorough description is that this problem has been addressed by many different authors, many different scientists, and each of those scientists have put out a conclusion to the problem that they've analyzed. From what I'm getting here, this person is basing so the problem that he is specifying is that there is a discrepancy between the redshifts that are detected across the surface of the sun and those that are predicted via normal redshift mechanisms, either Doppler or cosmological. Actually, in this case, it'd just simply be Doppler. So there's a discrepancy there. That's the case, and this is the discrepancy he's talking about. So a redshift so we're talking about discrepancies from the center, which would be here, 0. 1 would correspond to the very edge of the sun. And so this discrepancy is basically starts out at 1 part per million in the velocity in the redshift, and then it ramps up to about 4 parts per million in around the edge. So this is not a big effect. This is not a large effect. And this was discovered by M.G. Adams, apparently. So this analysis is based on observations or a problem detected by a single person. That doesn't sit well with me. Then when we go down here, like any good paper should have, and no, I'm not talking about matrices. So any good paper is going to have references. So let's look at Adams. This problem was recognized in 1948. This person is Alessandro is looking at the discrepancies found by a researcher in 1948. If this is truly an existential crisis, shouldn't there have been more recent observations? I'm going to assume there is, because this is obviously a problem. Somebody somewhere would have looked at this again before now. So why is it that they are only looking at a problem identified in 1948 and not sooner? And this is going to become a recurrent theme with all of Whitsit's evidence. If I were also to put on my, advisor hat, my graduate advisor hat, I would tell Alessandro, you don't need all of these graphs. They're redundant. They don't really inform us of anything. Really, the only graph you need is, or plot, I should say, is I don't know, a whole bunch of matrices. Jesus Christ. This is a mathematician's wet dream. Where'd it go? Oh, it's like figure 24. 21, 22. This one. This is the moneymaker. This is your money shot. What this is saying is, so you've got the black line corresponds to the redshift deficiency that Adams found in 1948. The dotted line is Alessandro's essentially fix. He's like, all right, the reason why this excess exists is because they didn't take into account the amount of energy, or people have not taken into account the amount of energy that is lost due to interactions with electrons along the field line of sight. So if you take that into account, his data or his analysis shows that he perfectly well explains the discrepancy that Adams found. Again, you have observations, or you have observations, or you have a model. So you have Adams' observations. He has Alessandro has his model. You match them up, and you see if they correlate. You see if they match. That match is great. I haven't dived into it, so it might be there. But one of the immediate kind of red flags I see here is no error bars. There is no statistical analysis of the quality of fit. It's kai by eye, as we say. It looks good, so therefore it must be good. I would kind of like a little bit more meat to it, statistical meat to it. All these other plots that he has in here, and he has like 4 or 5 of them. These are basically saying this is what my model says compared to Adams' model. If I don't take this into account, if I don't take that into account, well, obviously you want to take that stuff into account. No one is telling you that. No one has ever made the claim that granular motion on the sun's surface is not going to affect these things. So this isn't needed. But I chalk that up to inexperience of writing scientific papers. But like I said, I haven't checked the math, but I can tell you that the methodology is pretty sound in the sense that scrolling up. How about doing this? So he first starts off by talking about, all right, there's a whole lot of moving parts. All of those moving parts are going to produce a redshift, or going to affect the redshift. And he identifies, I can't think of a single one that he's not identifying. There is the gravitational redshift between the fact that the light is coming out of the sun, which is a massive body. He seems to take that into account. There's the fact that the sun is rotating. And it's also rotating. It's not a solid body rotator. It's a differential rotator. Layers on the equator actually moves faster around the pole than the poles do. So it doesn't rotate like a basketball. It actually rotates. It kind of gets what's the technical term I'm looking for? Twisty. That's the one. So the equator moves faster around the pole than the poles do. The poles don't stop. I mean, it's not that drastic, but so for example, if you were sitting at the polar or the equatorial regions, your sidereal day would be about 26 days. If you were near the poles, if you're around 60th, 70th latitude, your sidereal day would be about 30 days long. Hopefully that makes sense. Takes into account that. It takes into account the fact that the Earth is rotating, and again, your rotation is the amount of redshift is location dependent because we live on a globe, and the Earth is going around the sun. So he seems to be taking care of all of this stuff. He then goes into the description of his model. Here is the mechanism via which you would get, this is the mechanism via which that the energy is going to get lost. This is the line of sight, what's the word I'm looking for? The electron distribution that you're looking through. He's accounted for all of that. So yeah, top notch. Like, again, I don't know the math. I haven't studied it, but everything looks above board. This, I will grant you, seems to be legit. This is an open question. If what this person is saying, if all the math checks out and everything else checks out, and somebody else hasn't quite explained why Adam's observations showed that discrepancy, then, this is something seriously worth looking at. And if people aren't looking at it because of the reasons I alluded to before, that it's a single author, not trained in the field, if that's why it's not being looked at, that's a problem. I will fully admit that. This research, this idea needs to be taken seriously. And considering he is now a master's student at a university, I think his research is being taken seriously. Other folks are looking at it and giving their professional opinion as to what this is. And he has published 6 papers, all of which seem to me to be in reputable journals. I haven't done the due diligence on it, but they all seem legit. And they range basically from this to cosmological problems. So is Alessandro onto something? Is there a legitimate redshift problem that would indicate some kind of energy loss as light propagates through a field of electrons? Maybe. Sure. Okay. I'll give him that. This is the next paper that's on there. And this is, hey, Tina. And this is the other problem. So as I mentioned, the first problem was the solar disk redshift. And this has been addressed. And that paper that I just showed you was from, I think, 2021. So really recent. Everything else in this folder, everything else that actually has substance to it and not a diagram that looks like I need to get my prostate checked, or a screen that tells me, 7 quick ways to make a course or whatever. All the rest of this is not recent. Well, first off, you have this. Redshift anomalies are key to the understanding of dark energy, dark matter, black holes, and the unobservable universe. Okay, well, one, immediate red flag. Can someone I will put it to the audience. When you look at that, what is the first thing that comes into your mind? Do you want to trust that? And if you don't want to trust it, if you want to trust it, why? If you don't want to trust it, why? I do like to put on a good show. Oh, Austin is the agenda, essentially. Cygnus. So, but yeah, essentially this is actually sort of a review article. The first thing I will say, well, like I said, I'm posing this, so if you, I am looking for answers. If you look at this, and so all right, so Clive says it's a Word document, untrustworthy. He and I are simpatico on that. If anyone trusts this, please let me know and tell me why. It's a Word document. So I don't know about, well, this is astronomy. So yes, I do know about it. Scientific articles are not written in Word. They're written in LaTeX. It is one of the geek, I don't mean this to be disrespectful. It's kind of it is just in line with the geek mentality. It is literally a you are coding, you are creating a computer program to write a doc or to format a document. Word isn't good enough. We have to actually basically write computer code in order to format it. I'm joking. It's oversimplification, but yes, astronomers use a format, or basically a kind of a language called LaTeX, and it produces a very distinctive format. So no, what Whitsit is all about, Whitsit isn't about really proving a flat Earth so much. Whitsit really likes to nail down and to point out proposed or suspected problems in the accepted model, and then make the sweeping claim that because these problems exist, the entirety of the model is wrong. Which, actually, let me get into that now, because time is running a little short for me. This is something I found to be very common in the flat Earth community, or I guess now in flat Earth, concave Earth, university, electric universe Earth, is that folks in those communities will point to, oh, what about dark matter? What about dark energy? You can't explain those. Like, no, we can't. Those would be open questions. Open questions are allowed. What isn't allowed is contradictory evidence. Is that, essentially you need falsification. What they're pointing out are primarily uncertainties, things that we don't know, that we haven't been able to quite explain yet. But the existence of dark matter doesn't state that our understanding of relativity is wrong. All it states is that relativity at the present moment cannot explain what it is. That's more, actually, dark energy would be a far better analogy to this. Dark energy is not something that we expect in relativity. But does it falsify relativity? No, it does not. Relativity can exist with it, in the sense that the existence of dark energy does not state that relativity is wrong. It just states that that relativity is incomplete. So yeah, the idea of taking these gotcha moments, these gotcha little problems, not understanding them very well, if I'm to be honest, and two, then applying, basically making blanket statements. All right, you can't trust any of it. Like, no, actually, this is the good stuff. This is how you can know to trust it. It was thrown in my face, you guys keep changing the distance to the sun, man. First you say it's this, and then you say it's that, and then you say it's this. And I'm like, when have we done that? Eventually, he put up a meme, and the instances that he was talking about, Aristarchus, Ptolemy, Kepler, I think, or Copernicus was another one. I'm like, oh, okay. So people got it wrong hundreds of years ago, but now we ain't doing that. Now we have a fairly consistent distance to the sun. If there's discrepancies, they ain't huge. So yeah. Anyway, kind of gotten off the wrong start. Yes, dark energy is a cosmological constant, which is consistent with GR. Won't go too more far into that, because I have questions as to the cosmological constant was put in by Einstein based on basically as a fudge factor. I don't understand its physical. This is probably a problem for me. I don't understand the physical underpinnings of why it should exist. But yes, it is consistent with GR. But this is the good stuff. This is why science can be trusted, is because we are not simply brushing this crap under the rug. We are not ignoring this. We are not ignoring that, yes, we don't know what dark matter is. Yes, we don't know what dark energy, the cause of it is, how it really integrates into relativity. How is it that curved space-time results in dark energy? I don't think we have good answers for those, at least not definitely not for the first one. I don't think for the second. But these discrepancies, these problems are the challenges we must come up to, we must face. They are the ones that we must stand up and work on. And we are. If science were basically just shoving that under the rug and saying, hey, I don't need to explain everything that a model does, then that would be disingenuous. That would not be science. So, yeah, he said it was a blunder. Basically, the idea, and again, I could be corrected if I'm wrong about this. At the time, the prevailing idea was that the universe was static, that the universe was, depending on who you talk to, if you talk to Curtis, the universe was large. If you talk to Shapley, the universe was constrained to the Milky Way galaxy. But in either case, the universe was and always has been what we saw. Basically, it was static. And so when the main problem is that Einstein first faced, well, maybe not first, but obviously there's a problem with GR in that situation, is that if you do not include a repulsive aspect to general relativity, if you do not include that cosmological constant, then over a very short time scale, at least astronomically, that static universe is going to fall in upon itself. So there has to be something to balance gravity. And then Einstein said that it was his greatest blunder because Edwin Hubble came around and first showed that the universe is way larger than we thought it was, because the Andromeda Nebulae was in fact the Andromeda Galaxy 2 million light years away. He got the distance wrong, but close enough. And then he showed through his observations that the universe was, well, he showed the law. He showed that the velocity is equal to the Hubble law, or Hubble constant times distance. It's a very linear relationship. And so Einstein was like, oh, all right, so that problem goes away. Apparently it had some kind of initial momentum, and boom, no need for a repulsive force or a repulsive aspect. But NDT paraphrase. Please don't paraphrase NDT. Oh, I don't like the man. Anyway, getting off topic here. So what I wanted to say. So yeah, where was I going with that? Oh, another thing, just kind of going off on a slight tangent. I do want to get to this, but is that it really irritates me. It really irritates me. No, I don't dig NDT. Is when people put up posts or put up quotations of scientists, where the quotation seems to be contrary to the very thing that they came up with. So for a gross example, they'll cherry pick an Einstein quote that basically says that there is no optical observation that will allow you to tell that the Earth is moving because of relativity. The reason why I don't like that, the reason why it irritates me so much is, one, it's cherry picking. You are providing a quotation completely out of context. I don't know what was said prior. I don't know what was said after. I don't even know who it was he said it to and why. All of that matters for me to understand the meaning behind a short snippet of text. And two, as Einstein called his cosmological blunder, even really smart people can be wrong. For instance, Einstein wasn't kosher with, I guess that's a Jewish joke, wasn't kosher with quantum mechanics. Never believed in it. He did not believe that quantum mechanics was a thing or was right, because the if you want to pick a quote, God doesn't play dice. A, that doesn't mean he was religious, but B, basically is saying that his fundamental problem was that he was a determinist. He believed that the universe could be completely characterized. So the idea of chance, the idea of uncertainty in our knowledge was something he couldn't deal with. So he rejected quantum mechanics. So, all right, so and I think in this paper or some other papers, I think it's the other paper. Either way, one of these two gentlemen basically said, well, even Hubble didn't think that the redshifts that he was seeing were cosmological. Well, great. Okay, he didn't. He's wrong. He's allowed to be wrong. Even if he discovered these observations, you can find observations and you can categorize what you can posit what you think is causing those observations. Those observations can be right, and your explanation can be very wrong. That is possible. That happens in science. So cherry picking these quotes is dishonest, and it's dishonest in the fact that, like I said, it's cherry picking. And two, the fact that Hubble does not, because Hubble discovered that the universe is expanding, does not make him the absolute authority in all things cosmological. Because Einstein was the father of relativity does not make him the expert on all things relativistic, particularly things that we're discovering after he died. So if you really want to, get on, if you want to throw a quote at me or whatever, give me a paper. Don't quote mine for me. If you want to show to me that that this is wrong because Einstein himself said it was wrong, then show me his paper that shows this, that proves it, or that illustrates this. Don't tell me a quote. Don't give me a quote from a letter he wrote some dude back in the 1920s. I could care. I could give a shit, to be honest with you. Anyway, getting back. So yeah, this is written word. Immediately, like, what's going on? I don't trust this. Two, it's not even submitted anywhere. It's not that it's not submitted. It's not that it's submitted to a open journal that has no peer review. It's not submitted anywhere. And on top of that, I've Googled this name. I don't know who this is. I can't find them. I cannot find a cosmologist. So to me, this is a complete rando writing this. So maybe it's an appeal to authority fallacy, but why should I trust this individual? Then you've got this, dedicated to Holton Arp. Holton Arp, very sharp man, very intelligent, very good astronomer. Did not believe in the Big Bang theory from an ideological context. He was a firm believer in steady state, which is impossible because it would require, I don't know. I will resist saying that it would require violating the second law of thermodynamics. But what it would require is violating energy conservation. The steady state theory, in order to expand an ever-expanding universe, requires the spontaneous generation of energy, which is not physically possible. You have to rewrite the basic understanding of physics for steady state to work. But Alton Arp, steady believer. He was one of the pioneer, or one of the, not pioneers, but largest tent posts, largest proponents against Big Bang. And again, it's primarily from ideological basis. But he did find quasars or QSOs that seemed to not be congruent with the idea of the Big Bang. So this paper, which again, I will admit, I didn't go into a lot of detail, but it basically shows what I found elsewhere. And the idea here is that you take a normal galaxy, you take a normal galaxy, which has a redshift of a low redshift that indicates that the galaxy is close. And then you take a quasar or QSO that has a redshift, measured redshift that is much larger. And then you have some evidence to suggest that these two are gravitationally linked. That in this case, there is basically a tail, which is commonly seen in galaxies, where one massive object is literally ripping apart another massive object. And this becomes a stream of material you see from basically, in this case, it would be this larger galaxy is eating the smaller galaxy, and this stream of material is essentially the sort of the gravitational pathway that the particles, the stars and gas and dust are following. This is common enough anyway. But in order for this to happen, in order for this to exist, in order for that to be the explanation, these two objects have to be in the same locality. These redshifts would indicate they are in no way close to each other. Because again, the Hubble law, velocity equal constant times d. You can basically replace v with z. These two values are way different. If you assume a constant Hubble constant, then obviously the distances have to be way different. So you got that. Here's another example of it. Another one. And basically, you get the idea. You get the idea that that's the thrust of pretty much everything else that Whitsit has in this folder, is that ARP and his subsequent, I hate to use the word acolytes, but subsequent people, I guess students, like-minded individuals, they all really ARPed on this. Sorry, that was bad. They came back to this problem. They were like, this needs to be explained, because what's happening here is you have two objects. You have a normal galaxy and you have a QSO, which is an active galaxy. The active galaxy is moving away from us at really high rates of speed. Somehow it is being ejected from that system. And then we don't have a physical mechanism that would adequately explain why that would be the case. Why is it that these two things are moving away from each other? So, what ARP contended was that, again, more in line with what Whitsit is doing now, is that basically what ARP was saying was, given this discrepancy, the Big Bang Theory can't be accurate. It can't happen because we're seeing this. But now, like this person actually puts in something a little weirder. Basically, their idea is the reason why we're seeing such a larger redshift is because the gravity well is getting strengthened in these objects somehow. Again, I didn't read too carefully into this, but that quasar, I'm going to call it quasar, although technically speaking, there's a difference between a QSO and a quasar. One's a quasi-stellar object, the other one's a quasi-stellar radio object. Anyway, I'll get into those in a second. Yes, aliens. Aliens are causing the quasars to become more massive. And if you have something more massive, if you've been here from the beginning, what that indicates is that the cosmological redshift or the gravitational redshift, the gravitational redshift becomes larger. If you deepen the gravity well, the amount of energy lost by the light as it's traveling away from the object goes down. So the light gets redder, the redshift gets larger. So this person is explaining that discrepancy is actually due to the fact that the thing is getting more massive, apparently. The active galaxy is getting more massive. The normal galaxy is not. And in every case, and I do want to stress this, in every anomaly that ARP and subsequent papers that go for this show, is that it's always the quasar, which has the aberrant redshift, not the normal galaxy. So yeah, that's what this person says, is that it gets more massive. And, for someone who's posing that, gravity is getting weird, you know what is another red flag? Clive can probably see this immediately. What is completely lacking from this paper? If you're going to put forward an idea that something is getting much more massive, that the gravity is being strengthened, what is it that a scientist would want to see in your paper? The other person had it. Alessandro had it. Math. The answer is math. Yep, there you go. No questions. There's no math. There's no mathematical underpinnings to this claim at all. So, okay. So to me, it goes into the realm of, all right, nifty idea. But, I think that the Mass Effect games are really nifty ideas. They really should make a TV series out of the Mass Effect, the BioWare Mass Effect games. Really interesting concepts. That's science. But anyway, I've harped on this paper. I've harped on this paper too much. Yeah, I'm going to beat that to death. So I'm going to share my screen. I'll bring this back up. So we've got these papers. 2009. Redshift asymmetries, cold dark matter explains anomalous redshift. Again, this actually supports the Big Bang, so I don't even know why he included it. But again, 2009. It's 2023 for those who are keeping track. This is also 2009. This is a review paper, so first author, not a big deal, but is a conference proceeding. Conference proceedings in astronomy, and presumably in physics and other sciences, conference proceedings are not peer-reviewed. They are really opinion papers. They're either opinion papers, as this is, or they are, hey, look at this. We found this really interesting thing that we're going to follow up on. If you want to follow up on it too, contact us. Look at our wonderful stuff. Basically, it's a kid showing off a pretty toy. That's basically what it is. That's what a conference proceeding is. And this person basically goes through what I've just been kind of telling you, is that there is, when it comes to these galaxies, this ARP, that there is a discrepancy in QSOs. But what this paper also points out is that ARP kind of did a no-no. He did something that you don't do in astronomy. And that is, he had a selection bias. What he did was, presumably, by some chance, he found a QSO that was anomalous. He basically found, by probably looking for something else entirely, he saw a galactic pair where the normal galaxy was at a set distance or a set redshift, and the other, and the QSO or the quasar, which was right by it, had a completely different velocity, but the two appeared to be physically linked. Subsequent studies by the man have, his methodology was, okay, I'm going to look at other galaxies that have QSOs around them, or no, I'm going to look at other normal galaxies that are close, and I'm going to keep looking further and further away until I find a QSO that matches, or a QSO that fits my criteria. If I don't, I'm not going to tell anybody about it. So he may have found galaxies, normal galaxies, next to quasar. Well, actually, no, he wouldn't have. Quasars are, I really should tell you what a quasar is in a second, but he really wouldn't have found them. But his own what? All right. If he what he want, what he should have done, I think, is a study of quasars. He should have just done a blind study of quasars and seen how relevant this is. And that's the key question, is because in his studies, he's come up with a not insignificant number, I think on the order of a few hundred. But in comparison to the or less, I could be wrong. I see your question. I'll answer that in a second. But the first question you've got to ask is, how much of an anomaly is this? And the problem is, in order for you to answer that question honestly, you have to approach the question honestly. You have to say, all right, you have to not be looking for it. And that's what Art did. He specifically went after targets looking to prove what he wanted to see. And so, yeah. All right, folks, I actually need to go very soon, but there are two things that I want to say. I want to finish up on. I think you're talking about this paper. This paper was an ANA, great journal. Got nothing wrong to say about it, other than the fact that you have to pay them to publish your stuff. This is in, it's in, oh, and also I wanted to point this out. This is a crisis in cosmology conference. Again, this illustrates that astronomers understand that there are problems between observations and current theory. We have conferences to talk about it, to try to reconcile this stuff. Pay to publish, almost. So the main journals, this is kind of an aside, but so for astronomers, it's the Astrophysical Journal, or APJ. It's the Astronomical Journal, or AJ. It's the ANA, Astronomy and Astrophysics, or it's the MRAS, or Monthly Notices of the Royal Astronomy Society. Of those four, and there's Nature. Of those five, MRAS is the only free one. MRAS is the only one that is peer reviewed, but doesn't ask you for money. All the rest of them do. And yes, that is a problem. I don't like that system. It inserts a certain amount of bias into it. But anyway, we can have a discussion about that later on. But oh wait a minute, I got another hour. Anyway, so where was I going with this? So yeah. It's not like we sweep this stuff under the rug. It's not like cosmologists basically be like, oh, we made this stuff up, and if it doesn't work, we're going to ignore it. No, we address it. We get together. We talk about it. We figure out, all right, if this is the data, do we trust this data? And if we trust this data, then how do we make this theory fix it? Or how do we make this theory work with that data? How do we reconcile that theory with this data? And if we can't reconcile that theory, what theory can replace it? Do that all the time. That's how science works. Now, the reason why, and I do want to admit that I noticed something when I was going through, going through here, that I may have missed going halfway through. Going through this, apparently there's also apparently some kind of discrepancy in morphological type. So this is basically where it's apparently on this data sample, which honestly is pretty small. So I small number statistics. If you have a small data sample, the conclusions you can draw from that data sample tend to be a little bit suspect. Yes, I've talked to AB about that. I'd like to, kind of to piggyback on something that Matt had said. It would be interesting to get a panel together of AB, you, Clive, folks who've published, and talking about the practices in science and how it's not as egalitarian as we would like the flat earthers to believe. But anyway, I'm getting off track. So yeah, so apparently there is a little bit of evidence to suggest from Cepheid variables, which is a completely different from a different distance measurement or different measurement criteria than redshift from the Hubble flow. It's a lot more solid, I should say. There's a lot better evidence. Like it's a lot. I would, if someone gave me a distance using Hubble flow and someone gave me a distance using Cepheids, I'd go Cepheid 9 times out of 10. It's a much more tried and true method than Hubble is, because you can compare it versus many a number of different other distance indicators that you cannot do, that Hubble cannot be tested against. But anyway, apparently there is some kind of weird correlation or weird thing where the expansion rates, the Hubble constant is different if you look at a one type of spiral as opposed to another type of spiral. I again never heard of this. This was in 2009. Small number statistics, so I'm guessing, don't have proof, but I'm guessing someone looked at this and was like, "Yeah, that's weird. Let's use a larger data sample and see what we can find." And what they found was a reasonable explanation for why this is happening. But I wanted, for openness and for honesty's sake, I wanted to point out that I have not addressed this. I did not really look into this. So this might be an anomaly that Whitsit puts out there that I haven't fully dealt with yet, or thoroughly. That's not what I wanted. All right. Let's see. So another paper. Oh yeah, I already did that one. Let's see. Redshift, Plasma Universe. It's a web page, which will pop up eventually, I guess. Oh, maybe it is popped up. Plasma Universe. Actually, this just goes through. Oh yeah. This is actually useful. This basically, this page goes over the various different types of redshift. It refers to cosmological redshift as theoretical, which I have a problem with, or it puts it into hypothetical. I have a problem with, but it goes through NASA ads, and it says, all right, how many papers are out there that show the word, that have the phrase intrinsic redshift in the abstract? So this is NASA ads. If you want to know the Witless anomaly, if you want to get, there's archive, which is basically where papers go before they get officially published. So and they're free, so you can get them, but technically some of them haven't been officially peer reviewed. So there is that kind of caveat to it. With NASA ads, you can get to the papers themselves. Some of them are behind paywalls. The more recent ones are probably behind paywalls because, as said, they kind of suck. But some of them aren't. But yeah, so NASA ads. This is what, if you want to Google it, this is the database of, just Google that. You can get to the database of scientific papers related to astronomy. So if you have questions or you're curious, you can just click on this, intrinsic redshifts and the Hubble constant. This is only, the paper was never published. It's only an archive. That's kind of a red flag. It doesn't even look like it's submitted to anything. It looks like it's just, and that's something else that folks do, is they write a paper, they will submit it to archive with no intention of getting it published in a peer-reviewed journal for reasons which you have to wonder about. This is 2003. I have not read this paper. 2019, measuring the absolute total intrinsic redshifts, surface gravity plus the convective blue shift. This is not an anomaly in the sense of, well, this isn't an anomaly. This is, so we know surface gravity, we know convective blue shift exists. That's because there are cells. I talked about granulation before when we're talking about the other side. The surface of the sun is not a solid body, obviously. It's a giant ball of gas. And given the temperature of that gas, of that star, the upper layer of that star, the internal chemistry is such that the best way for energy to be transported from beneath to the surface is through a convective action, boiling. So hot plasma rises, it releases its energy out into space. That gas then cools off, goes down to the bottom of the convective layer, heats up again, repeat. Wash, rinse, repeat. That's going to affect your redshift measurements, is that convective action. Because obviously part of the surface is coming at you, part of it is going away from you. Oh, I know I'm kind of rambling at this point, but one of the problems I had with that Alessandro's paper was that he gave he said convection is on the surface of the sun is going to give you a redshift of 1,000 meters per second. That is a hell of an assumption, which I don't think is valid. But I don't have, that's a knee-jerk reaction on my part. If there is any glaring problem with the underlying physics of Alessandro's paper, it's the fact that he assumed granulation has a redshift of 1,000 meters per second. All right. I don't know where you got that from. But yeah, my point here, the reason why I'm bringing this up is non-cosmological redshift. This is part of Whitsit's evidence for why there are anomalies. Non-cosmological redshift. 2004, 1989, 2008. Don't know what that is. There was one that I thought was really kind of cool. My point here is this actually works against, I know it's a surprise, this works against Whitsit's argument, is that A, the papers here are either very old, which to me sends the message of this hasn't, if this was really a problem, there would be more recent work on it. And two, the papers that are here, almost all of them do not seem to indicate that there is an anomaly in place, or their use of the word anomaly is used differently, as in this is not what we would expect it if we just took this particular physics in line, not to say that there's a cosmological issue with it. There was one paper in here, and I don't think I can click and find it. It's actually a paper I want to go back and read. This is why I'm putting this together. Is it this one? No, I don't think it's this one. So when we look at the velocity of galaxies, we see this Hubble flow on larger scales. If you were to look at the velocities of galaxies in our local group, within 10 million light years, if you looked at the velocities of those and you compared them to the distance, you would not see a correlation, because the expansion of the universe is small with respect to the overall motions of the galaxies. All things in the universe have their intrinsic motion, or what astronomers call a proper motion. And that proper motion varies in amplitude. But typically proper motions, there is an upper limit. Typically things do not move so like redonkulously fast because of either gravitation or supernova events or what have you, any sort of non-expansionary physical reason. Those proper motions, there does seem to be an upper limit to how fast things just naturally go. So if you were to plot those up, it would basically be a scatter plot. You couldn't do what Hubble did and basically plot up a linear relationship. But if you like further out, then what happens is that the expansion outward due to the Hubble flow is larger than those peculiar velocities. Those peculiar velocities essentially then become part of the noise. They become part of the error bar. So you have you might have a galaxy that is intrinsically moving towards us at 200 kilometers per second, but because of gravitational expansion, it's actually moving away from us at 10,000 kilometers per second. Then obviously the expansionary velocity is going to cause the peculiar motion to be dwarfed. You're not going to really see that peculiar motion in there. That's what kind of causes the scatter in there. Yeah, I need to look into Dr. Becky. She rejected me, man. I asked her to be on my show. She was like, no, I politely declined because I'm in England, and I don't. The time difference would suck. So I'm like, I would love to have her on my show, but she rejected it. Darn it. Anyway, the paper I was going to show that I want to read that I will eventually find is actually, it's a test of general relativity, which is friggin' awesome, because we are now getting to the point where we have, and really the Big Bang of the expansion at small scales. Because we're getting velocities precise enough, we can actually start taking relativistic effects into account on local scales. So this paper was a proposal on how one would conduct that experiment. So again, it illustrates that within the community, these anomalous readings, well, in this case, it's not even anomalous. These are basically redshifts that are not, the reason why it's in this list is because the redshifts are not cosmological. So it's probably in here. They're not cosmological because it's not part of the overall expansion of the universe. And so, so the idea, the paper posits an experiment to use these peculiar motions of these galaxies to illustrate that relativity is a thing, that relativity is correct. So I know, how dare she? She should be honored to be on my show. Anyway, so yeah, that's the point that I wanted to make on that. So going back to this. So yeah, so all right, so he's got a folder here, all images. These are plots taken from somewhere, probably one of the papers that he has. I'm assuming that this stuff is debate fuel or debate fodder. Puts this into a PowerPoint presentation or slaps this up on the screen, and then misrepresents it, that sort of thing. So really, there's not really anything there. Like I said, there's this. Oh, Gary's back. Yay. So that's not really helpful. So yeah, there's not really a whole lot in here. There's only a few papers. And like I said, the ones that do, that's what it was. When I did go through this, a lot of the papers that seemed to be on point to what he was talking about, were again papers by ARP or people who subscribe to ARP's idea that these do not show, or these contradict the Big Bang Theory. These papers are all from the 70s and 80s. Again, yeah, I say that I often tell myself, watch out, Dr. Becky. Dr. Rob is coming for you. I don't even have 500. But yeah, so if you go into this, if you actually get in, or go to the website and actually dive into this, you'll find that the problem that it has is the same. It's a lot, maybe lots of different examples, but it's all the same anomaly that he's talking about. It's this all anomaly about the quasars. Now, what is a quasar? A quasar is a type of active galactic nuclei, or AGN. In brief, what we believe is that there is a supermassive black hole, and I would love, I'm just imagining what Gary is going to have to say to this, is there's a supermassive black hole at the center of every major galaxy. And by supermassive black hole, we're talking about a black hole that weighs millions, if not billions, of suns. Now, it's in every major galaxy. We have observational evidence to suggest that these exist there. Here we have observational evidence not only of there is a supermassive black hole within our own galaxy, not only from dynamics of stars moving around it, but we have now subsequently imaged the environment of that black hole. But the first image of the environment around a supermassive black hole was that of M87. M87 is an active galactic nuclei. What that means is that if you took the entire energy output from the center of that galaxy, that energy output exceeds the entire energy output of the entire galaxy combined. So more energy is coming out from the center of that galaxy of M87 than everywhere else in the galaxy combined. And this is a location that can be shown through variability studies has the size of the solar system. Tiny. So the energy in a galaxy constrained to the area of a solar system. Aladdin just popped in my head. Incomprehensible power, itty bitty living space. So there are galaxies like that. We know from looking at the characteristics of a galaxy, looking at them over various wavelengths, like I said, variability studies, we know that these galaxies are different. We know that there is a tremendous amount of energy coming off these things that does not happen with other galaxies. Like, for instance, and the reason why that is because you have this supermassive black hole, like I said, and then you had what? Okay. You have the supermassive black hole, and you have this accretion disk, this massive disk of material, of dust and gas. And it's moving around in a Keplerian way, in the sense that Kepler's laws tell us, and really classical mechanics tells us, that the inner parts of the disk are going to move faster than the outer part of the disk, which is going to cause shearing, which is going to cause heat or energy production. And it's that shearing, that massive disk moving against it, shearing against itself. It's creating all this energy. The difference between the M87 and us, our galaxy doesn't have, or our supermassive black hole isn't eating. Doesn't have that disk to feed on. M87 does. It's eating the material in that disk, creating so much energy. If we did have that disk, I question whether or not we would be here. Because again, the energy output of our galaxy would at least double if that turned on. So hopefully that never happens within our lifespan. So about 20% of all galaxies within our local environment, where we actually can find all the galaxies in what we call a volume limited sample, we are confident that we are properly getting all of the galaxies that can be seen, that exist within a certain volume. 20% of those are active galactic nuclei. Now, active galactic nuclei come in a whole slew of varieties. You got your Seafords, you got your Blazars, you got your Liners, you got your Ulurgs, you got your quasars. All of these are real, and quasars specifically were found in 1963 by a gentleman by the name of Schmidt. And what was peculiar about this was that it was the high redshift. He found lines that should have been in, I want to say, the UV part of the spectrum, in the red part, in the infrared part of the spectrum. It's been a while. I probably have that wrong. The point is, the redshift of line, he found lines of a chemical species of hydrogen where he should not have found them, because they should have been way higher energy than where he found that. And when he looked at the source, when he imaged the source, it was quasi-stellar in that it didn't look like a galaxy. It just looked like a really blobby star, hence the name quasar. So what we believe that quasars are, the current idea of a quasar, is that it is an active galaxy that is very young. When the universe is small, or when the universe is young, the universe was small. And so interactions between the galaxies happen very quickly. Interactions between galaxies happen very often. And they cause basically what that means is that when galaxies collide, they're going to send a whole lot of material out, but they're also going to send a whole lot of material in. And so presumably these supermassive black holes, or something akin to them, formed first. That merging or interaction sent material into those objects, or into the centers of those galaxies, and those massive black holes started eating a buffet. They just started munching on all this material and just got really, really bright. So that's basically what a quasar is in a Cliff Note sort of way. Is a very young, active galaxy where you have a black hole that is producing a whole lot of energy, or where a whole lot of energy is being produced around it by material falling into that black hole. Now, this is kind of where, again, from a scientific point of view, you got to scratch your head. Because what Arpis and his followers have found is that this redshift discrepancy, that that there are galactic pairs with disparate that seem to be in the same position of sky. There are some doubts to some of those, but some do have compelling enough evidence to suggest that they are in fact local to each other, where the quasar is moving really, really fast and the normal galaxy isn't. What that would indicate is the quasar is much closer. And so the mechanism behind how that quasar came into existence is, I'm sorry. No, scratch that. That's completely wrong. It actually indicates that it's very, very far away. But yeah, there's this discrepancy. Where I was getting to that was it only happens with QSOs. It only happens with quasars. We don't see this with normal galaxies. So there is the issue that normal galaxies, because of how bright they are, or rather how lack of brightness they are, we can only see them at a certain distance. So quasars are the ones that really allow us to plumb the cosmological distance scales, but we don't see it in normal galaxies. Now, I want to show you something before I go off and teach some youngins how to find a comet using ye old analog finder charts. I want to show you this. So redshift studies have been done for a really long time. We have done massive studies, ground-based massive studies of galaxies all over the sky. One of the popular ones, images out of this, is this one, which I think is pretty awesome. Oops. It's that. What you're looking at here is, obviously, we are at the center. Each one of those dots corresponds to a galaxy similar to the Milky Way. This is observed data. This is not a model. This is not a simulation. This is observed data. This disk, this ring around it, is basically stellar longitude. You can think of it, 8 hours is in one direction, 12 hours is another, 16 hours is in another direction. The reason why there's this wedge shape is because we reside in a galaxy that has a lot of dust and prevents us from really looking past it. There are observational reasons for why, there are observational selection biases for why we don't see these particular regions. But we can see these regions of space from actually, yeah. And this is but one slice. This is, as I said, the circle represents longitude. This is actually a thin slice. I don't know, does it actually specify? This is a wedge. If you were to look at this in 3 dimensions, it's actually a wedge. So there's a range in declination or a range in latitude. A buddy of mine, when I was a grad student, actually did a really, really small scale version of this with lucite and dots and stickers. It was cool. But anyway, yes, this is the Sloan Digital All Sky Survey, or Digital Sky Survey. So all of these indicate dots. All of these, and each dot indicates a galaxy. As far as we know, we don't see anomalies in this. There's no indication that the basic methodology behind redshift and distance is wrong, given all of these. Now, that's a picture. I like numbers. I think Clive likes numbers, although I think he likes equations. I'm going to show you something. Again, give you a little in the know for astronomers. You can Google something called Simbad Astronomy. Simbad Astronomical Database. Really cool. Go by, and basically you can search for stuff. This is our big, huge database run by the French. It's got some problems, but overall, really, it's an invaluable tool. So I can go to an identifier, and I could say Andromeda. Nope, actually, let's do this. My favorite star in the whole world, Lambda Andromeda. There it is. There it is in the sky. I can get its coordinates. I can get all the lovely magnitudes. I can tell you, it can tell me the parallax, which tells me the distance, all sorts of groovy stuff. What it's called in a whole bunch of different catalogs, measurements that people have taken about it, references. Like if I want to look at the papers that have been published, I can go through here. All of these have reference to Lambda Andromeda. Excellent resource. So if you're really interested in any particular object, go there. Vizier. So you just believe whatever he spits out. You got a reason for Gary? It's kind of like put up or shut up. At this point, you have basically called me a liar. So either you need to present evidence for why what I'm saying is factually wrong, or you have to supply evidence, or at least a motivation, just a motivation for why I have dedicated my life to lying to everybody. So, yeah. So Vizier. Vizier is a catalog of catalogs. So let's do this. Speculations of a confused astronomer. No, everything I'm saying is the work the work that has been done by the astronomical community since time immemorial. So focus, Rob. Focus. You're almost at the head. You're almost at the finish line. Vizier. So you go to Vizier. Type in SSDDM. Boom. You get a whole bunch of catalogs involving the Sloan Digital Sky Survey. I'm going to choose release 16, which was released in 2022. This survey, again, science is never done. Science is never completo. We never say, oh, we're done. Let's go do something else. I don't remember when the first digital sky Sloan survey came out. It was a while ago. This is the 16th version. They keep refining it. They keep adding to it. Now, how big is this survey? Well, that's an excellent question. I will answer that question for you. This survey contains information on 469,050,976 objects, stars, galaxies. 469 million. We have studied these. Now, obviously, because of I've only got it set so that I'm only showing you 50. But here's the first 50. And I'm only selecting a certain amount of columns. Here's the magnitude data. Actually, what is this? Photometric, and these are the redshifts that we've got. We've got redshifts going on. So we have redshifts to these things. Now, so obviously there are certain stars in here that don't have redshifts. So let's just look at spectroscopic redshifts. Let's look at the number of stars it's got that we have fairly reliable spectroscopic redshifts for. We've used the spectra. We've actually done what I've been showing you with the redshift of lines, spectral lines. We've looked at their shifts, and we've calculated the velocities and redshifts based on that. How many of these objects, how many of these 469 million objects do we have reliable data on? Well, I can tell you that. I go down, and there it is, spectroscopic final redshift, and I type in, give me all of the objects with redshifts greater than 0.01. There are objects in here that either do not have a redshift or have a redshift of 0. Essentially, what that tells me is that the redshifts are not well defined. So I'm getting rid of that. Fairly reliable. And so I here we go. Pretty much 469 million. So ARP, and the whole crux of this, Whitsit's argument, or Whitsit's data here, the crux of it is, and I haven't found it, but I can tell you that the number of quasars, the number of disparate wavelength or disparate redshifts that have been found, on the order of scores or possibly hundreds of objects. Yes, that is significant and should not be ignored. And I'm sure it hasn't been. But you know how many objects there are that have redshifts that are not anomalous? 460 million. So yeah. Again, we have Occam's razor in a way of you have some objects that are questionable, but you have a vast trove of observations that are in line with theory. So simply stating that these anomalies basically cancel that out, I find to be, I don't see the logic in it. I don't see how that's possible. Well, not possible, but it's like you're giving credence to these basically open questions, because in and upon themselves, they don't nullify the process of, or they don't nullify the expansion of the universe as we understand it currently. They just simply are unexplainable by that method. They don't falsify it. They simply cannot be explained by it, which is a distinctive difference. Distinctive difference. And there are hundreds of millions of objects that can be explained properly with the Big Bang model. As I showed you before, there was one of the cool things that we discovered with this is that the universe is filamentary. And this, you can see the isotropy, and you can see the isotropy and the inhomogeneity of the universe in this. This is redshift data. This is and basically distance data. Well, actually, no, sorry. This is just redshift data. This is basically expansion. We can see that this is the velocity expansion of galaxies from us. Again, it's specified that the cosmological principle, it says that the universe is isotropic and homogeneous on large enough scales. So obviously, if you look over here, you're going to see, whoops, you can't see that. So if you look over here, yeah, all right, this doesn't really look homogeneous. It's a big bright point and kind of a void. That doesn't look homogeneous. But if you look at all of this and you compare it to all of this on large scales, it's homogeneous. And if you look at any particular direction, I challenge you to find a direction where it appears that there is a preferential structure, that things seem to be emanating from that particular point. An example of what I mean by that is if you're on the top of a hill over a flat plane, when you're on top of that hill, everything seems isotropic. Everything seems flat. But get off of that hill and move over to the side and then look everywhere around, you're going to notice the hill. You're going to notice that preferential location. Here, we don't see that. And unless you got a really good reason to explain why we happen to be on the only hill in the universe, then I might be willing to listen to you. So yeah, this is the evidence that folks want to just get rid of. Just want to, it's not there, doesn't matter. It's hundreds of millions of data, hundreds of millions of data points that we use to come up with this, to be used as evidence for what we say. Astronomers, cosmologists, we're not some kind of weird club that gets around, smokes weed, and comes up with, hey, wouldn't it be cool if the universe was expanding? That would be awesome, man. Like, mind-blowing. No. Do we reject people who basically say, hey, the universe isn't expanding. The earth is flat. We're the center of the universe or whatever. I'm hoping that this here is showing you, no, we don't. I am honestly and hopefully objectively, as much as I can, trying to address the issues that Austin Whitsit had, or the evidence that Austin Whitsit has for cosmological anomalies. And as I said at the top of the show, what I'm showing you was given to me by a third party. So this, I could be misrepresenting what Austin is saying, but it is consistent with things that I've heard him say verbally. So I have addressed this. And again, when it comes to the solar stuff, maybe there's something there. I don't know. I'd have to look into it more. But the cosmological with the quasar stuff, is it a nail in the coffin of the Big Bang? No, it's not. No. I am the center of the universe. So, all right. Let's see. This is pathetic and sad. All right. Thanks for the judgment. Many of them have timed me out too many times. I've counted various chats where they were mods. There's no different from blocking someone. I don't want you blocked, Gary. I don't want you timed out. I would like you to have the courage of your convictions. I mean, if you're going to sit in basically a crowd and accuse me of lying, of misrepresenting, then I would like you to actually have a conversation with me. A conversation, not you throwing shots across the bow from a comment section or from a comment section or a live chat, because honestly, I think that's cowardly. That is a cowardly way to behave, and so may seem like I'm a bit sensitive about that, and I am. This couple weeks or couple days, weeks, whatever, haven't been the greatest. So maybe I'm making more of this as a more of a mountain out of a molehill. But I take umbrage at being told that this is pathetic and sad. So please have the courage of your convictions to actually discuss things with me, and so that I can understand why it is you think that what I'm telling you and what I tell everyone else is either pathetic and or sad or rubbish or whatever the hell it is you accuse me of. Okay. Well, I don't know if that went as coherently as I intended it to. It was, as I said, meant as a legitimate addressing of Whitsit's arguments or his claims that Redshift cannot be used. It has been the Redshift anomalies have debunked Big Bang Theory. That the CMB has debunked the Big Bang Theory. Like I said, I've been trying to be honest and straightforward about it. So who knows? He could be, but I think one of the reasons why I'm a little bit more adamant about this is that I've seen Gary around, in certain chats, and he's never been a dick, and until now. So, I'm a bit peeved, put off by that. So I hope I've succeeded in what I wanted to do in showing, in describing these things and provide, and I hope people have gotten some kind of, have learned something about the universe and things of that nature. So, and lastly, I will say, I hope, I say it here, Whitsit and his acolytes are going to start throwing out tired light theory to explain cosmological redshifts. If people push on this, if people ask them about obviously cosmological evidence directly contradicting the electric universe idea, he's going to start putting out tired light theory. All right. If you like this sort of content, please like, share, and subscribe. Again, I plan on doing Coffee and Science as often as I can, and I will try to get guests on as much as I can, but primarily what I think this is going to be is I'm going to look for those open questions. I'm going to be looking for those things that we can't currently explain, and I'm going to expound on them. I'm going to give you my insight on it, tell you what the problem is, give you my insight on it, tell you how big of a problem I think it is, and whether it really needs to be addressed. I think the next one I'm going to do is I'm going to address, there was maybe a few months ago, there was this brouhaha about observations done by the JWST, which have debunked the Big Bang Theory. I'm going to look further into that and illustrate why those claims are problematic. So I am now going to go off, get something to eat, I think, and then teach some of our tour guides how to find the Great Green Comet through a small telescope. If you would like to support our outreach program here, please consider becoming a patron of mine. You can find the Patreon in my About page. All proceeds go to the observatory. I'm actually about to go take some stuff I bought with Patreon money, some kits to hold eyepieces, some headlamps so they can actually work with their hands in the darkness. Yeah. Oh yeah, Gary, we're going to be using equatorial telescopes to go track a comet. It's going to be awesome. All right. Thank you all. And again, apologize if it got a little bit weird there at the end. I'm still a little bit raw. But yeah, I'll see you all next time. Oh, and if you want to pass this around, promote my channel to folks that are battling against Whitsit and Co., feel free to send them over here and let them know. So, all right. Peace out. Clear skies. See y'all next time.